Okay, here we're going to look at oscillations, which is basically a mass attached to the end of a spring. We're not really covering anything new here. We're just applying F equals ma to different situations. Earlier, we simply looked at examples of constant forces. That gave us the kinematics that we used earlier in the year. We're also going to apply it to air resistance, and that's what gave us this relationship that ended up giving us a terminal velocity. We also will look at what happens if the force follows an inverse square law. And this is what Isaac Newton showed, is that the resulting solution basically are conic sections. And this is the equation for a conic section, where E is the eccentricity, and that depends on the energy of the system. Will the solution end up looking like a circle, an ellipse, a parabola, or a hyperbola? But now what we're going to do is take and say the force will follow Hooke's law. So if the force follows Hooke's law, what does the position as a function of time look like? Well, it's going to end up being an oscillation, and the requirements for an oscillation are: first, you must have some sort of a stable equilibrium with some sort of a restoring force. The restoring force we're going to look at will be a Hooke's law force. We also need little to no friction, because if we get too much friction, we'll end up with what's called an overdamped system, or the friction, if it's so much bigger than the restoring force, will not let the system oscillate at all. If we have less friction, so the friction is small compared to the restoring force, it will oscillate, but the oscillations will become damped. The mathematics is a little more complicated, and we simply won't have time to go over that. However, to set the object into oscillation, we do have to somehow disturb it from its equilibrium position. This could be by giving it some initial velocity, or it could be by simply starting it some position away from the equilibrium. Now, we also want to look at briefly what exactly do we mean by simple harmonic motion. Well, first, of course, it is a periodic motion, but a ball bouncing up and down elastically on the ground is a periodic motion. It, however, is not represented by combinations of sines and cosines, so we don't call that to be harmonic motion. What's graphed right here is harmonic motion, and what we have is basically a sine function with two different frequencies, and in fact they differ by exactly a factor of 2, which means they are harmonies of each other. And if we do that, we get a nice periodic motion that does repeat itself, but it is not simple in that you can see it has some internal structure to it. This is, for an example, what a musical note might look like if you play both a note and one of its overtones. By simple harmonic, we mean it's represented by simply one trig function that has one frequency. So this could be represented by just a sine function. This is its single frequency. It may or may not start oscillating at x equals 0, at t equal to 0, which is the purpose of this, what's called a phase angle. But this is what simple harmonic motion looks like. The way we get that is we basically take a mass and we put it on a spring, and the spring will follow Hooke's law, and we're going to analyze this just by using F equals ma, where the force is just Hooke's law minus kx. We're going to replace a with the second derivative of the position, rearrange that, and we have a differential equation for x. Now, the way we're going to analyze this is to figure out what kind of function might solve this equation. To do that, we're going to say the form of this equation is basically the second derivative of x is a negative number times the position of the x itself. And we're going to take the simple case, what if x is, k over m is 1. So the second derivative is just minus x. What kind of function solves that equation? Well, we're going to look at it qualitatively first. And by this, we're going to consider what is the meaning of the first and the second derivative. Well, the first derivative, of course, is just the slope. So here we have a curve, and the slope is just the tangent to the curve. In this case, the tangent is not always in the same direction. It changes. And in fact, here it goes from being positive to being 0 to being negative. So it is changing and getting smaller. So we say the rate at which the slope changes, which is the second derivative, is negative. And this is what a curve with a second derivative that's negative looks like. It is curved downward. And basically the second derivative is what gives us the curvature, the shape or the bending of the curve. We also, of course, can have one that opens up, and this is one that has a negative slope that then becomes larger, goes to 0, and then becomes positive. This is an example of a positive curvature. Now notice this right here does in fact mimic roughly what it is we want. When x is positive, we want the function to have a negative curvature, a negative second derivative. When x is negative, we want to have a positive second derivative or a positive curvature. This is what will give us the oscillation, so that when the function is positive, it has to curve down. When the function is negative, it has to curve up. And that will be roughly what matches the second derivative is minus the function. And that will give us a function that oscillates. So what we're going to guess is our solution will be some combinations of sines and cosines. Take this function right here and take its second derivative, and that's what we get is the second derivative of this is minus omega squared. We get an omega coming out. We take the derivative of both the sine and the cosine. Take the second derivative of the sine, we get a minus sign. We get a second derivative of the cosine, we get a minus sign. I factored that out right here. What's inside parentheses right here is just x. So the second derivative of this function is just minus a constant times x. If that constant is in fact the k over m, or omega squared is the square root of k over m, we have a function that solves our equation. Omega is what is called the angular frequency. It gives us the period. The period is 2 pi over omega. We plug omega in here, and we get that the period is 2 pi times the square root of m over k. The two constants a and b are determined by the initial conditions that set the oscillator into motion. Remember, that was another thing we needed. The initial position is just the constant b, and the initial velocity gives us the other constant, a. Notice, again, we do have this alternative solution where x sub m will just be the amplitude of the oscillation. Notice a and b combined will give us the amplitude of oscillation, but neither of them are them directly. X sub m is the amplitude, and phi is this phase angle that determines what is x at t equal to 0. Now, next thing we're going to look at is the energy of our oscillator. The energy will in fact be a combination of kinetic energy and potential energy. We want to see how does this energy change as a function of time. X, we already have the solution for x. V we get by just taking the derivative of x. So first derivative of this is this. Take V and plug it in here for kinetic energy. Take x and plug it in here for potential energy. A little bit of algebra then gives us E as a function of t is just 1/2 k times a squared plus b squared. Notice there is no t in here. So therefore, E as a function of time is a constant. All of these are constants, or energy is itself conserved. Another oscillator we can look at is, rather than a horizontal oscillator, we can look at a vertical oscillator, in which case the force is the force of gravity, which is downward, it's the minus sign, and we also combine Hooke's law. This is the equation we want to solve. The way we're going to do that is by changing the variables. So rather than solving for x, we're going to end up solving for y. So we take this x and we replace it with this expression. Notice this right here is just the new equilibrium point, the point where the spring pulling up and gravity pulling back down counterbalance each other. So we're going to solve for when does that equal to 0, and that is our equilibrium point. And y will be, it'll oscillate around this equilibrium point. So we take the x in here and replace it with y. This is what we end up with. This equation simplifies because this term and that term cancel out. So on the other one side of the equation, we just end up with minus ky. Taking the derivative of this right here, that's a constant. So all we end up with is m times the second derivative of y. Well, that's the exact same equation we had before. So y has the same solution that we had before, and nothing really has changed. A vertical oscillator will oscillate exactly the same as a horizontal oscillator. It's just its equilibrium position is not at x equals 0. Another example of something that oscillates is a pendulum. A pendulum will swing back and forth, and what we want to look at is a pendulum an example of a simple harmonic oscillator? The way we're going to analyze a physical pendulum is using Newton's second law in the form of torque equals I alpha, where the torque will be given by a component of gravity, gravity pulling straight down. This right here, this torque, this component is the component of the force that's perpendicular to the lever arm. Here is our pivot point. Gravity acts at the center of mass, so h is the distance from the pivot point to the center of mass. That times this component of gravity is the torque. If the angle is positive, the torque will be negative, so that's why we have the negative sign in here. That equals I times alpha. Alpha is just the second derivative of the position, which is the angular position, theta. And so this right here is the equation we want to solve. Well, here we're going to take a look at what happens if theta is fairly small. If theta is fairly small, what we can look at is here is a graph of the angle as a function of the sine. If the angle is small, namely between 0 and 15 degrees, turns out the sine of the angle is very much equal to x if x is measured in radians. Up to about 15 degrees, the two curves pretty much align exactly. They begin to diverge at a little bit at around 20-25 degrees, but even then, the difference is only about 3%. So that for small angles, the sine of x is very close to being equal to x. And that is what we're going to take advantage of. So for small angles, I can replace this sine of theta with just theta, and then rearrange and collect terms on one side. And this right here is the same equation we had before, so it'll have the same solution. So for small angles, a pendulum approximates a simple harmonic oscillator, where the angular frequency is given by this, and we take and rearrange it, and the period is given by this. Now what we're going to consider is what if we have a simple pendulum, which consists simply as a very light string with a very heavy mass at the end. The mass right here we will take to be small compared to the length of the string, and the string will be very light compared to the mass m. The setup here is identical to the setup before. The difference is that all of the mass will be at the center of mass right here. This will be equal to the length of the string L right here. The setup is otherwise the same. We're still using torque equals I alpha. We're now H, which was the distance from the pivot point to the center of mass, is now the length of the string L. The moment of inertia is just ml squared. So the period is the same expression we had before, but now I becomes ml squared, H becomes L, one of the L's cancels out, the M cancels out, and the period is just 2 pi times the square root of L over G. And this again, so long as the angle is small, less than about 10 or 15 degrees, this will behave very much like a simple harmonic oscillator.